Hey folks, my name's Nathan Johnston. Welcome to lecture 17 of Advanced Linear Algebra. Today we get to start a brand new topic, which is inner products. And then later on in this week, we're going to look at orthogonality, which is based on inner products. Okay, so the idea here is think back to when the only vector space in sight was Rn. In other words, think back to when you're in introductory linear algebra. We had an operation on Rn called the dot product that let us look at all sorts of geometric properties of vectors. In particular, it let us look at the angle between vectors, and also it let us look at the length of vectors. Okay, and we'd like to be able to do those things again, but in arbitrary vector spaces now. Okay, so right now what we're going to do is we're going to introduce our generalization of the dot product to arbitrary vector spaces so that we can start doing things like talking about the length of vectors or the size of vectors in general vector spaces. Okay, so here's the definition to get us running, this definition of an inner product. And again, when we generalize these things to arbitrary vector spaces, we're not going to define them via an explicit formula or anything like that, but rather we're going to define them via what properties they satisfy, okay? So an inner product is just going to be any function that satisfies certain properties, just like a vector space was any set of vectors that satisfied certain properties, right? Okay, so what is an inner product? Well, if you have some vector space V over a field F, and in this case, when you're working with an inner product, we're really going to need to be working with the real or complex numbers, okay? I'll talk about why that it is in a minute, okay? This does not work over arbitrary fields. You need real or complex numbers. Okay, then an inner product on that vector space, it's a function, and then this funky little notation here means what this function does is it takes in two vectors from V and spits out a number, okay? So this V cross V, that's the input, two copies of V, and then F is the output. Numbers are the output. Okay, so first off, your function has to take in two vectors, spit out a number, and also it's got to have a bunch of additional properties, and in particular, these three additional properties down here for it to be an inner product. The first property that it's got to have is what we call conjugate symmetry, okay? And this just means if you swap the order of the input, so if you change V and W to W and V, then what happens is you pick up a complex conjugate over top of the inner product, okay? So it's not quite symmetric. You can't just swap the inputs freely, but you have to be careful, throw in a complex conjugate if you swap the inputs, okay? If the field that you're working over is the real numbers, then of course the complex conjugate does nothing. So in that case, conjugate symmetry is the same as symmetry. But in general, if you're working over complex numbers, don't forget the complex conjugate when you swap. Okay, the next property that we have is an inner product. It has to be linear in its second entry. In other words, if I leave the V fixed in the first entry, then it behaves kind of like a linear transformation in the second entry, right? We have W plus CX splits up into a W plus CX. Okay, so it acts linear in the second entry of the inner product. And then the third and final property that you have to have is something that we call positive definiteness. And what this is if you plug in the same vector to both slots of the inner product, you always get a real number first off. Even if you're working over the complex numbers, you get a real output from this. And not only a real number, but a non-negative real number. And even furthermore, the only way that you get zero is if you plug in the zero vector to both slots. Okay, so in other words, if you plug in any non-zero vector, you get some strictly positive real number here. Okay, so there's a lot to unpack in this definition. Before we even get going through some examples of this, let's answer a couple questions that are probably floating in your head, like why do we do these things? Like why is this defined this particular way? So first off, I said I'd come back and talk about why we need the real or complex numbers. Like why is that? And that is because in general fields, like if you have some other number field other than real or complex numbers, you might not have an order. You might not have an order of those numbers, right? You might not be able to say, hey, this number is bigger than this number. Even in the complex numbers, actually, we don't have sort of a natural field ordering, okay? But we sort of need one, right, for this property C here to make sense. We need to be able to talk about the output of this function, which is in the field, being bigger than or equal to 0. Okay, so the reason that this works with the real numbers is because there's a nice ordering on the real numbers. The reason that it works with the complex numbers is because this quantity here, even if you allow complex outputs in general, whenever you plug in the same input to both slots, you always end up getting a real number anyway. Okay, and that follows from conjugate symmetry, actually, okay? Because if you swap the inputs, nothing changes, but you also pick up a complex conjugate. And in other words, V inner product V is always going to be real because it equals its own complex conjugate. Okay, another question that pops up when you look at this definition is, well, why these three properties here? Why properties A, B, and C? And of course, the reason for those three properties is because we want this to mimic the dot product on Rn, right? And if you go back to introductory linear algebra, right after you saw the dot product, you would have seen properties that looked exactly like this, except written using dot product notation rather than inner product notation. Okay, so it's just like vector spaces. We define vector spaces to mimic Rn. Well, we define inner products to mimic the dot product. Okay, one thing that you have to be a little bit careful of is property B here. Inner products, they're linear in the second entry. They are not quite linear in the first entry. You can use conjugate symmetry to show that they're kind of linear in the first entry, but not quite, okay? So if you use conjugate symmetry to try to figure out what happens if you have V plus Cx inner product with W, in other words, what happens when you have a linear combination in that first entry there, well, you swap things with conjugate symmetry, property A, and then you can split things apart using property B, linearity in the second entry. And then, hey, these are all just numbers, and I can pull the complex conjugate onto each of the inner products individually. And when I swap them back, when I swap this inner product back, the complex conjugate goes away. And similarly, when I swap this one back, the complex conjugate goes away. But one complex conjugate that never goes away is the one over the scalar here. Okay, so what happens is if you have V plus Cx inner product with W, you get V with W plus complex conjugate of Cx with W. Okay, so it's almost linear, except you picked up complex conjugates over top of scalars. So it's what we call conjugate linear. Okay, so you can sort of split up linear combinations in the second entry, and you can split up linear combinations in the first entry, but only as long as you remember to put complex conjugates over your scalars. Okay. And now let's look back here. I said that we introduced these three properties so that these inner products, they would mimic the dot product. But wait a second. I mean, in the original dot product, like the original dot product on Rn is just symmetric, right? V dot W is the same as W dot V. So why did we throw this weird complex conjugate over top here? Where does that come from? Okay, well, think about what would happen if we didn't have that there. Well, plug in any non-zero vector into your inner product then, and what you're going to get is, hey, inner product of non-zero vector with non-zero vector, that's got to be bigger than 0, okay? So I just took whatever non-zero vector I like and multiplied it by I, and then here I use property C to see that this is bigger than 0, strictly bigger than 0. Okay, but now if property A didn't have that weird complex conjugate in it, I could just pull each of these scalars out and I wouldn't need to throw complex conjugates over either of them. So I'd end up getting an I squared over out in front rather than an I and a minus I. So I just get I squared out in front, and I squared of course just equals -1. So I get a -1 out in front. But now I'm left here with minus the inner product of V with itself, and because this inner product of V with itself must be strictly positive, negative of it must be strictly negative. So what we found here is that 0 is strictly less than some junk, which is strictly less than 0. So 0 is strictly less than itself. And that, of course, cannot happen. Okay, so there's no way to define a function that actually has all of these properties but without the complex conjugate there. Okay, you need the complex conjugate to actually find functions like this. Okay, and because we only have this weird conjugate linearity in the first property, we sometimes call these functions sesquilinear, which just means 1.5 linear. You know, it's linear in the second entry, and you know, it's sort of half linear. It's kind of linear in the first entry. Okay, so let's go through a bunch of examples of inner products on various vector spaces that we've been working with. We, of course, have already seen an inner product on Rn, right? Just the dot product. So that's just an exercise to go through to check, maybe convince yourself that, yeah, the dot product on Rn really is an inner product. It satisfies those three properties from that definition up above. All right. Well, a very similar inner product exists on the vector space Cn, so complex numbers, but n of them in a list. Okay, and this is actually also called the dot product. Okay, it's called the dot product on Cn, or the complex dot product. And what it is, well, it's just you do the same thing as in the dot product. You take all the entries of V and W and you multiply them together and you add them up, except you throw a complex conjugate over top of the entries in the first vector. Okay, and maybe we haven't seen this notation before yet. This V star here, I'm thinking of V as a column vector. The star means transpose it, so turn it into a row vector, and also put a complex conjugate on every entry. Okay, so this is just a different way of writing this exact same formula here. Okay, so if you don't like that, just remember this. It's the same thing. Okay, So let's show that this actually is an inner product. Let's show that this complex dot product really is an inner product. And the way you do that is you check the three defining properties in the definition of an inner product. So the first property to check is that if you swap the order of the two vectors in an inner product and put a complex conjugate over top, then you'd better get the same thing as just the original inner product itself. Okay, so let's just check using this formula for the inner product. Okay, so W inner product V, well, that's just the sum of the WI's with a complex conjugate over them because they're the first vector in the inner product times the VI's, and then you add them up, and there's this complex conjugate here just over top of everything. Okay, and if you have a complex conjugate over a sum, you can just put that complex conjugate over top of every entry in the sum. And then over on the left here, we've got complex conjugate of a product of two numbers. Again, complex conjugate, it splits up over products, so it's the complex conjugate of each of them individually. And then the WI's have a double complex conjugate over top of them. And complex conjugating twice just gets you back to where you started. So WI conjugate to conjugate just equals WI itself. So we're just left with this sum here. And if you just swap the order of the terms here, so you have VI bar times WI, you see this is exactly the complex dot product itself. It's the inner product that we started with. So yeah, this left-hand side does equal the right-hand side, so we're happy with that. Okay, property A is satisfied. Property B, you just plug in the linear combination into the second entry, and then you plug all that back into this definition of the complex dot product. So you got VI bars, and then the ith entry of the second vector. Well, the ith entry of the second vector is WI plus CXI. And then, well, those are all just complex numbers, so you can use your usual arithmetic rules in with complex numbers, right? This is a sum of a product, and then there's a sum here. Just distribute things, okay? So you get a sum of VI bars, WI's, and then this sum over here, and those are just the individual dot products, okay? So nothing fancy happens there. It's just your usual arithmetic rules, just sort of n times, because there are n terms in the sum. Okay, and then finally, property C, we've got to show that the inner product of V with itself is bigger than or equal to 0, and furthermore, the only vector that gives you 0 inner product with itself is the 0 vector. All right, so the way that you do this, again, plug into the definition, right? It's just my W's are V's now. So I get sum of VI bar VI, and one of the nice properties about the complex conjugate is the complex conjugate of a number times itself just equals the length or magnitude of that complex number squared. Okay, so you've got a length squared that's bigger than or equal to 0, and then plus a whole bunch of other lengths squareds also bigger than or equal to 0. So the whole thing's bigger than or equal to 0. And furthermore, the only way that this sum can equal 0 is if each of these lengths equals 0. In other words, each VI has to equal 0. In other words, V must be the 0 vector, right? Each of its entries must be 0 for that sum to equal 0. All right, so that's the whole thing. That shows that, yes, this function up here, this complex dot product, really is an inner product. And we call it the standard inner product on Cn, just like we think of the dot product on Rn as the standard inner product on Rn. Okay, but there are lots of other inner products as well, though we'll see more of them as we go, but it's good to be really familiar with these standard examples. Okay, so let's go through another example on a slightly more exotic vector space. This time we're going to be working with the vector space. We use a curly C here to denote set of continuous functions, and the set of continuous functions is a vector space. Okay, we haven't worked through it explicitly in these lecture videos, but it is. Okay, and this square bracket a to b, that means I'm only considering the continuous functions on the real interval from a to b. So I'm not considering how they behave on the entire real line. I'm only considering how they behave on that interval from a to b. All right, so on this vector space here, let's show that this function here is an inner product. Let's show that if I integrate the product of those two functions from a to b, I get an inner product. And before we go through why this is the case sort of rigorously by checking those three properties, let's think sort of intuitively about why this feels like an inner product. Okay, the only examples that we've seen so far are the dot product. And for the dot products, what you do is you take one of the vectors and you multiply it by the other one, but just sort of entry-wise, and then you add them up. Well, what are we doing in this example here? Again, we're multiplying the two functions together entry-wise, and then in a sense, we're sort of adding them up. It's just the function version of adding, right? We sort of have infinitely many points to add up. Roughly speaking, the way you do that is via an integral. So again, like this should feel sort of like the dot product, okay? So it feels like an inner product. All right, but how do we actually prove that properly? Well, again, just go back to the definition of everything. You gotta check these three properties. I have to check conjugate symmetry, but hey, it's a real vector space, so it's just symmetry. Is the inner product of G with F the same as the inner product of F with G? And yeah, it's just, hey, one of them's an integral and the other one's an integral, and they just have the order of the function swapped. So in other words, you're just multiplying real numbers in the opposite order. So yeah, that's true. All right, property B, can I sort of take out linear combinations in the second entry? Is it linear in that second entry? And again, yeah, this just follows from properties of real numbers and integrals, right? Here, okay, so this is the integral that we get if we plug this stuff into the two slots of the inner product here, okay? And then, hey, again, fx times gx, so gives me that first term, and then I distribute. I get a c times f times h, and I get that, and I can split it up into two integrals because you can do that with integrals. If you have an integral of a sum, that's a sum of integrals. Okay, and then hey, this is one inner product, that's f with g, and then this is c times f with h. So again, nothing fancy happening there. Okay, property C is slightly more interesting because property C, okay, inner product of f with f, that's the integral of f times f. So in other words, it's the integral of f squared. Okay, great. That's bigger than or equal to 0 because each of these numbers is bigger than or equal to 0, and then I'm integrating that function. So you're integrating a function whose graph is above the x-axis. All right, well, that area under the graph is going to be bigger than or equal to 0, right? If the function never dips below the x-axis, its integral can't be negative. You're measuring an area that's above the x-axis. So yeah, this is bigger than or equal to 0. But furthermore, like we need equality to happen if and only if we're talking about the 0 function. Okay, and that is true because, well, sort of roughly speaking, think about like how could this equal 0? Well, each of these things, they would have to equal 0 for the whole integral to equal 0, right? Because again, you're adding up, roughly speaking, all of these pieces above the axis. Okay, so the only way that this whole integral could be 0 is if each of these is equal to 0. In other words, if f of x equals 0 for all x. Except you have to be a little bit careful there. I lied a little bit there. This is why we need to work with the vector space of continuous functions, okay? This is why we're only considering continuous functions. Everything that I just said there is wrong if you go outside the realm of continuous functions, because you can have annoying little things like a function that's 0 everywhere, except, hey, it takes on a value of 1 at 3. When you plug in x equals 3, its value is up at 1, but everywhere else it's down at 0. That function's integrable, and it has integral equal to 0, basically because like there's just not enough weight. Even though it eventually at one spot it's up at 1, it's not up at 1 enough to actually affect the integral, but it's not the 0 function. Okay, so we really do need to be working with continuous functions here for this to be an inner product. Okay, otherwise things get a little bit murkier. All right, so those examples, those are all standard inner products on the spaces that they act on, okay? But there are also lots of non-standard inner products as well. So let's look at a non-standard inner product on R2. And by non-standard, I just mean sort of not a usual one, not one that's going to come up over and over and over again or anything like that. Okay, so let's try to convince ourselves that this weird ugly function is an inner product on R2, okay? So it's just sort of, again, it's kind of like the dot product, except we've got weird weights in there. And we've sort of got cross terms as well. It's not just V1W1 plus V2W2. It's sort of nastier than that. But it is an inner product. Okay, so properties A and B, maybe I won't go through those because they're sort of just straightforward. You just check the definitions. Is W inner product V the same as V inner product W? Yeah, you just swap everything around. And because these two coefficients here are the same, everything works out, okay? And similarly with sort of pulling linear combinations out of the second entry, it's just use your usual laws of arithmetic on Rn, well, on R2. Sorry, on R, okay? They're just real numbers that you're adding up here. Okay. The interesting property is property C. Is this function non-negative if I plug the same vector into the two slots? Okay, so what do I get if I plug the same vector into the two slots? Well, here I'm going to get a v1 times v1, in other words, v1 squared. Over here I'm going to get 5v2 times v2, in other words, 5v2 squared. And then each of these cross terms is going to give me 2 times v1 times v2. Okay, so I'm going to get 4 times v1 times v2 as my overall cross term from these two terms. Okay, that is not obviously bigger than or equal to 0, but fortunately we can rewrite it in a way that makes it obviously bigger than or equal to 0. And the trick is to factor things so that it's a sum of squares. It's this cross term that makes it not obviously bigger than or equal to 0. So factor it into some factor that has this as its cross term when you expand it out. In other words, what I'm going to do is I'm going to say, okay, I want some term that when I square it out, I get a v1 squared, and I also get this cross term. All right, and the sort of binomial that works, the binomial that does the job, is v1 plus 2v2 all squared, right? Think about what happens if you expand this out. I'm going to get v1 squared, and I'm going to get double this times this. So I'm going to get 4v1 v2. So I get the cross term. All right, the final term isn't quite right, but it turns out that's okay. The final term, I'm going to get 4v2 squared. I want 5v2 squared, so just add on another v2 squared. And then this is really good, right? Because I've got something squared plus something squared. Yeah, great. Squared things are bigger than or equal to 0, so when I add them up, bigger than or equal to 0. Okay, and furthermore, remember you have to check, when do I get equality here, okay? Is the 0 vector the only vector that actually gives me equal 0 here? Well, the only way that I can get this equal to 0 is if both of these terms, them squaring and adding up, equals 0. So in other words, v1 plus 2v2 has to equal 0, and v2 has to equal 0. But hey, if v2 equals 0, then over here we get v1 equals 0 as well. So the only way that it can happen is, yeah, if it's the 0 vector. So that weird function there really is an inner product. It's an ugly one, but it is one. Okay, that will do it for our introduction to inner products. I will see you all next class when we look at the standard inner product on the space of matrices.